Welcome to the next video in our SimpleCPU Games Console video series. And this video we'll be looking at our video display controller's block copy and block write commands. Right, and so the video display controller has two block commands. It has block copy and block write, as you can see here. Their descriptions are on this web page if you want a little bit more detail. But basically the video display controller is obviously a raster display. It breaks the display down, it breaks the image down into a series of lines. So within that display line, you can write a block of color, and that block can be over multiple lines. So the way to think about it is that the video display controller's frame buffer is just a block of memory, a block of sequential memory addresses, and each memory address contains 2 pixels color codes. Therefore, the block write command just writes the same color code to a block of sequential memory locations. So the pixels associated with those frame buffer addresses will be set to that color. One of the primary use cases for the block write command was to allow the user to clear the display. So if you write the color code for black, basically the value 0, from frame buffer address 0 all the way up to frame buffer 160 times 120 minus 1, you will write to every single pixel and you'll set all those pixels to the value 0 to display black. So it's a nice easy way to initialize your display, to clear your display. But it can also be used to block out blocks of color, as in the tank game, as in combat, as we saw in the first video. So if you block out kind of the maze regions in that game, the borders, this command is also very useful. And to support that, I implemented a macro called draw box, where you could draw a square or a rectangle of a certain dimension. And we'll see that in 2 ticks. However, before we do that, a key point to note. As I've highlighted in previous videos, the frame buffer is organized as a 16-bit storage location. So each address that you write to will update 2 pixel values. So on the line that you're defining this block of color, you will be updating pixels in blocks of 2. And those pixels will be aligned to even numbered addresses. So memory is arranged, as I say, in blocks of 2 pixels. So address 0 in the frame buffer will contain the pixel color codes for pixels 0 and 1. Address 1 in the frame buffer will have the pixel color codes for address 2 and 3. So if you do a block write command and you were to write to pixel 0 or pixel 1's frame buffer address, you would update pixel 0 and pixel 1 to the same color. Now that's confusing, but hopefully it will become clear when we look at some examples. So here's a graphical representation of our display. We're zoomed into the top left corner. So pixel 0 you can see here is in row 0 and column 0. And the top 2 pixels in our initial image, our test image that is loaded into the frame buffer before boot, we have a block of 2x2 red pixels in that top corner, as we've seen in the photos in previous videos. So the data for this row is broken down into blocks of 2, broken down into 16-bit values. So the first pixel colors are in frame buffer address 0, so pixel 0 and pixel 1. And then in frame buffer address 1 is pixels 2s and 3s. Then in address 2, we have pixels 4 and 5. So when you tell the video display controller to a block write, it will update a block of pixels within that row, within that line that is writing to the display. And by repeating that over a series of rows, we can draw rectangles, squares, that will form part of our display. So to help illustrate that, we have test program number 5, and within that program, we can draw boxes, we can draw graphical elements of various sizes, but I've just stuck 2x2 pixels, keep it simple. So we can draw a green square, a yellow square, a blue square, and a pink square. So within our graphics library, we have a macro called draw box. You pass it the color of the box you're drawing, so green in this case here, the top XY position, and the bottom XY position. And it will draw a block of color in that defined space. So if you look here for the first example, so we can see we have the green square top left pixel is in column 4, row 6. Column 4, row 6. And the bottom XY position is in column 5, row 7. Column 5, row 7. And the video display controller will draw a color of that size. And it can draw a square or rectangular shape of any size, but its minimum width is 2 pixels. As that's 1 memory location's worth of storage in the frame buffer. Actually, I'll take that back. It's not any size. The size along the row is allocated in 2 pixel blocks. As each time the block write command writes data to the frame buffer, it will be updating 2 pixels worth of color codes at a time. So the size along the row is a multiple of 2 pixels. But because we're drawing a raster line, then obviously the resolution going down the screen in rows can be at a pixel's resolution. So if you look at these examples, we can see the green square is perfectly fine. Its top left X position is the value 4, which maps to frame buffer address 2, which is fine. And its far right position is column 5, so that is 1 memory location's worth of storage. So we're not crossing frame buffer boundaries here, so that's okay. Same for the yellow box, that is starting at 8 and 9, so that is 1 frame buffer's worth of memory location. The pink and the blue boxes are slightly different. So if you look at the blue box, in the code, it defines its top X position as being pixel 1. Now that isn't aligned to even address boundaries within the frame buffer. An even address boundary would be address 0, address 2, address 4, address 6, etc. So the way the video display controller handles that, it looks at which frame buffer address it will be writing to. So it'll be writing to address 0, and within there's obviously pixel 1 and pixel 0. So it draws the square to the left rather than drawing it to the right, as we had in the previous example. And the same for the pink square. So again, the user hasn't aligned the square to the frame buffer boundaries. So it will write the data to pixel 4 and 5. So again, a slightly out of focus picture of the screen of the FPGA running this program. We can see our red square in the top, which is from the initial frame buffer's initialization, and our 4 drawn squares using the drawBox command. Interesting, a little bit distortion on the blue pixel, pushing the edge. We seem to have some artifacts there. I'm not sure why that is so. I think it may be due to alignment issues. A final example to help illustrate the use of the drawBox command. I've added this extra command. So here we're drawing a white block, and it's starting at pixel position 4 on the top row. So top X position is 4, top Y position is 0, and bottom position 6 and 0. So it's on the same row, which is fine. But again, we're allocating pixels in blocks of 2. So this block here defines a 1x3 block. So pixel position 4, 5, and 6. But if we're writing to pixel 6, therefore we've got to write to pixel 7 as well. So you get a 1x4 block. And that's the main limitation of the block command. The rows, you have to allocate things in blocks of 2. Now, the drawBox command uses constants, as you can see here. So we specify the color and then the XY positions as numbers, which is fine when you're blocking out the initial maze in that combat game, for example, things that won't change during the game. However, if you're using the block command to define a 2x2 pixel block of color that is the ball in Pong, then that will need to vary its position over the course of the game. So you'll need to store the XY positions as variables rather than as constants. And to allow you to do that, I wrote the draw rectangle subroutine. And you can pass this graphical library unit the color, the top X, the top Y, the bottom X, and the bottom Y values as variables stored out in memory. In this example here, we're defining a rectangle of 6 pixels by 3 pixels, a bigger block. We could do exactly the same draw functionality using the drawBox command, but then that would be fixed, that would be static throughout the game. By drawing this graphical block using the draw rectangle command, we can then alter these variables and move its position around throughout the game. So again, if we look at our badly shot photo of the screen, we can see all our different blocks. So our green, yellow, blue and pink squares drawn by the drawBox command, our new white rectangle, also drawn by the drawBox command on that top row, and our larger 6x3 pixel block drawn by our draw rectangle command. And obviously by choosing the correct values, you can also draw a square. So the name's not particularly well chosen, but that's the name I chose. The final command we'll be looking at today in this video is the block copy command. So using the block write commands, we can update those frame buffer pixel values. But once you've done that, you may want to replicate certain regions of the screen. So rather than going through that process again, we can instruct the video display controller to copy a block, to copy an area of the screen to a different position. And the intention there is that obviously the frame buffer already has the data, so you don't have to transfer that data again. So it will be a lot faster. And I saw that possibly being used when you're setting up that initial background. So once you've kind of created a piece of the terrain and you want to replicate that across the screen, you can simply do that by using the block copy command. So for example, we've gone to the trouble of drawing this nice pattern on our screen. Rather than cutting and pasting the same code to redraw these shapes elsewhere on the screen, because remember the draw box command uses constants, so you can't put that in a loop because the XY positions are fixed. So you have to manually retype out the same square information but with different offsets. Obviously you could implement a loop using the draw rectangle command, so you could define the colors and the shapes that you wanted and then apply an offset to the variables that they use. But it's far simpler just to use the copy macro. This allows you to copy a block of graphics from one area of the screen to another. So within the copy box macro, we define the top and the bottom XY positions of the block we want to copy and the starting position of where it's going to. So the block I want to copy is from starting at position 0, 0, which is in the top left corner. And we're going to go all the way down to block 10, 10. So this square here. So I'm defining a square, a block from column 0, row 0 to column 10, row 10. And I'll be copying that, the starting X position, pixel 20, Y position 0. So basically alongside that block. So again, the top left pixel position, the bottom right pixel position, and the top left destination position. Again, I tried to take a picture of that on the actual monitor, a little bit out of focus, but you can see that that block has been replicated next to the original just by using that copy block command. In some respects, the block right command may seem a little bit limited in that you can only define 2 pixel blocks within a row. But for most games, that's not so bad. I mean, here's an example of the Pong game. So the net down the middle is 2 pixels wide. The bats are 4 pixels wide and the ball is 4 pixels wide. So you can see it looks reasonable. So even with these constraints, you can still implement a basic game. In fact, everything on the screen except for the 2 scores, the 0 and 0s are tiles, is implemented by the block right command. And in the game, as the ball moves or the bat moves, you'd reset the color back to the background color using the draw rectangle command, update the ball or the bat's variables to the next XY position, and then redraw that rectangle. Obviously, the game logic ensures that the bats and the ball don't cross the playing area boundaries, and when the ball does cross the net, we just simply redraw the net. Obviously, there's no problem drawing a block on top of another block, just the foreground block will overwrite to the background block. In that case, the net will be overwritten by the ball as it travels across it. Okay, I think that's where I'll leave this one here. So that is our block write and our block copy commands that can be used to implement simple graphics, as you can see here. If you do need finer level control, if you did need to manipulate individual pixels, then we have the draw pixel command, which allows you to do that, but it's a little bit slower. And if you wanted to draw a higher level graphical element, a line, again, we have a software library that will do that for you. And that can be drawn at the pixel resolution. So you can have a line made up of single pixels if you desire. Right then, so the next video I think I'll be looking at tiles. So drawing a tile and overlaying a tile. So in this screenshot here, that's what draws the player's scores, as you can see at the top there, the 0 and the 0. Okay, until next time.